Okay, guys, so a very good morning to all of you. So, today in the lecture number 12, we are going to discuss about again the abrasive jet machining operation or jet machining processes, we can say. So, from the last two class, we are discussing the same process, lecture number 10 and the 11th we discussed. So we started with the principal part. We discussed the working of this abrasive jet machining. Then in the last lecture, in the before after that after the working, we discussed about the modeling of material remold rate. And in the last lecture, we completely discussed the numerical portion of this abrasive jet machining processes. That is how this material removal rate exactly will be formed. Okay, by using as we are mentioning the assumptions, that is the complete kinetic energy is converted into the is used to remove the material. Okay, so we are assuming that this complete kinetic energy will be equals to the work done by the abrasive particles. Okay, so through that basically we derived the many formulas, and in the last lecture we derived the formula for the material removal rate when we are using the ductile material as well as when we are using the brittle material. Okay, guys. So today in this session, we are going to discuss. We are just moving forward, and we are going to discuss about how whatever the parameters that we are taking. Okay, so how it is affecting the material remold rate. Okay, basically there are number of parameters. Number of parameters are there, but three are very important. So that we are going to discuss today, and then we will take the numerical problems. Okay, so whatever numerical problems that is available to me, whatever I have found, so that we will discuss. Okay. So let's start. Okay. So first is there are three machine characteristics that we are going to discuss today. So first one is basically we are discussing means machining characteristics means we are going to draw a graphs. Okay, but these graphs will be between the material removal rate and the other characteristics, like mixing ratio is there, abrasive flow rate is there, standoff distance is there. Okay, so on the basis of that, we are just comparing these values to the material removal rate, that how material removal rate is actually affecting by these varying these parameters. So that we are going to discuss. Okay, so first one will be the mixing ratio. Mixing ratio we have already discussed, and I will also discuss today itself in a detail. Then we'll go for the abrasive flow rate. Abrasive flow rate. Third, uh, we'll discuss about the standoff distance or nozzle tip distance also, we can say. Okay, NTP. So this is we are going to discuss first, then we'll discuss the numerical problems. Okay, guys. So first, the machining characteristics between the material removal rate versus mixing ratio. MR I'm writing. Okay, so this is mixing ratio. Okay, so what is the mixing ratio exactly? How we can write MR, that is mixing ratio, that is equals to, we have already discussed, I have already told you in the process parameters when we are discussing about that. So mixing ratio is equals to volume, flow rate of abrasive grids upon the volume flow rate of gas or air, we can say. So mixing ratio is like we start the mixing ratio in the mixture only, basically this mixing is done. So this is a mixer. Okay, this is a mixer, we can say. Now from this side the air is coming. Okay, from this side the abrasive particles is coming, or abrasive grids is coming. Okay, abrasive grids, and this is air. So in the mixture basically only we are mixing this abrasive grids, we are releasing, then the high velocity or high pressurized air is coming into contact with this abrasive particles and the mixing is takes place. Then only we are taking into the hoses, and they are transferring to the nozzles, and then they are impinging over the workpiece surface. Nozzle is just we are using to improve the velocity, increase the velocity in case needed. Otherwise we are just keeping the whatever the velocity that is coming through it that has been maintained by the air. So this complete kinetic energy is converted, this pressure energy is converted into the kinetic energy, and this kinetic energy, this abrasive high velocity abrasive particles is only impinging over the workpiece surface, and they are removing the material. Okay, so now if we are talking about the graph, like how the material removal rate will change. So this is the material removal rate and this is mixing ratio. Okay, so this is y-axis and this is x-axis. So initially, like mixing ratio means, for an example, just I'm taking this example to that I just want that you should understand very in a clear manner. By the way, this example is not available anywhere, so I'm just taking a simple example. Just assume that like 100 particles of abrasive particles, this volume of this mixer, okay, not mixture, it's mixer. Okay, so the volume of this mixer will be equals to the 100 abrasive particles, 100 abrasive grit particles can be accommodate into that volume. Just we are assuming that 100 abrasive particles can be accommodated as at the same times in that mixer. Okay, so that is the volume of this mixture. Now if you increase, if let's suppose that this is connected with the hoses and that is connected with the nozzle, so just assume that there is one abrasive particle. Okay, there is you we have entered only one abrasive particle. We have entered only one abrasive particle. So here the gas is already coming. Okay, means 100 abrasive part, the volume of that mixer is equals to that 100 abrasive particles can be accommodated. Now only we are entering one abrasive particles. It means that 99% of the volume that is covered by the gas or air, we can say, right? So if one abrasive particle is coming, then one abrasive particle will flow as it is leaving the this mixture. The second abrasive particle we are passing, okay, in the mixture. So it's like only one by one particle is coming into this mixture. So how it will impinge, like one abrasive particle that will impinge over the workpiece surface. After that there is another abrasive particle, after that there is another particle. This is a chain. But let's suppose that at the same times we are mixing two abrasive particles. Okay, so two abrasive particles means these are in like contact, like we cannot say like these are in same plane. It can be one over other, but it has at the same time it is released, so there is no gap between them. Okay, so we can say like two abrasive particles is impinging over the workpiece surface at the same time. Okay, like just suppose that three abrasive particle, four abrasive particle, five abrasive particles, that depends that how much abrasive particle can be releases. If we are increasing the abrasive particles, no doubt these abrasive particle will come together and they will try to impinge over the workpiece surface at the same time. But again that depends on that how much nozzle diameter we have to maintain. Okay, so if we are increasing this abrasive particles, if we are increasing this abrasive particles, then the impingement over the workpiece surface is increases. It means the material removal rate will also be increases. Okay guys, so the material removal rate with respect to the mixing ratio, if we are increasing this abrasive grids, then no doubt this is directly proportional to the mixing ratio, so the mixing ratio will also be increases. If the mixing ratio is increases, then the material removal rate will also be increases. Okay, but this is not up to this one only. Now let's suppose that 50 or 50 abrasive particles we are entering together. Okay, now if we are at the same time we are like we are passing this 50 abrasive particles, then it means that only 50% a volume of this mixer is remaining, means that is covered by the air. Okay, high pressurized air. Now just increase this ratio. Increase this ratio means just increase this abrasive particles. Let's suppose that make it 90 or 100. Okay, then what is meaning is this 100, if you are taking 100 abrasive particle at the same time, it means that the volume of this mixture is completely full. The volume of this mixture is completely full, means there is no space where this gas can be accommodated. If this gas cannot be accommodated, then what will happen? Obviously, no, it has a very high density, it has a very high pressure gas, so it will try to come inside, but there is no volume, so it will try to basically break the surfaces. But is just assume that if it is coming with the whatever the 100 abrasive particles are there, they will basically move in this direction. But is the volume of the gas has been reduced, it means that the velocity of this air will also be reduces, because in the beginning, like only we are taking whatever the like 2 bar pressure we have maintained initially. Okay, so this 2 bar pressure is taking only one abrasive particle at the same time. Okay, now after that there is a two abrasive particle. Now it is taking 100 abrasive particle at the same times, and there is no space in the mixture. So what will happen? It will just push them. Getting my point? It will just push them, and they will not impinge over the surface, because it's not kind of bombarding. It's kind just they will basically, it's a kind of shower of these abrasive particles. Okay, shower of this abrasive particle over the workpiece surface. If it is a shower, then how we can expect that there is a material removal rate? Okay, so it cannot be possible. So if we are going to increase, if we are increasing this abrasive grit particles beyond a limit, then this ratio is decreases, then this ratio is decreases. Okay, please keep in mind, at a some specific rate of abrasive particles we are increasing, it will become maximum, but after that it will decreases, because the volume of the air is also that much important. It's not only this mixing ratio is independent, is only depend on the abrasive grades. It doesn't mean like that. Okay, it depends on the volume flow rate of the gas as well. If we are decreasing the volume of this gas flow rate, then obviously the kinetic energy or the velocity of the abrasive particles that has attained, that will decreases. If it is decreases, then it will not be a like removal of the material. Okay, it will just shower over the workpiece surface, and that just flatten. Okay, so please keep in mind, this is the graph for the mixing ratio with respect to the material removal rate. Okay guys, so if you have any doubt, you can ask me here. Okay, no doubt. Let's move to the next one. So next is related to this one only, because first one that was based on the mixing ratio, second is based on the abrasive flow rate. So here is also like we are defining this mixing ratio by the volume flow rate of the abrasive grids and the volume flow rate of the gas. So here this volume flow rate of the abrasive grids, that is only the abrasive flow rate. Okay, so it will be like the same kind of relationship. That is second is machining characteristic with material removal rate with respect to or versus the abrasive flow rate. Okay, so the same thing like uh, this is material removal rate and this is abrasive flow rate. Abrasive flow rate. Okay, so if like same thing, same concept that we discussed, because there we were discussing about that how this abrasive particles is directly proportional to the mixing ratio. So we were talking about in that basically the mixing ratio, but here we are talking about only the abrasive flow rate. Okay, abrasive flow rate means if we are increasing this abrasive flow rate, that is abrasive grit, we can say that is mass flow rate of abrasive grit, or volume flow rate also you can write. So if okay, so this is if we are increasing the volume flow rate of the abrasive particles, okay, then the same thing. It will not be a bombarding. It will be a just shower of that. Okay, so it will be a same. If we are using single abrasive particle, then the velocity that is attained by the means the velocity that is maintained by the gas. Okay, okay, that is by the gauge. So that will increases the velocity or the kinetic energy of the abrasive particle. But as we are increasing this abrasive flow rate or the quantity of that, then it will for the time being it will become, it increases. Okay, but after some time it start decreasing. Okay, so the same graph for both. Okay, abrasive flow rate and the material removal rate, sorry, mixing ratio, okay, with respect to the material removal rate. Let's move to the third one, which is a standoff distance. Okay, so this is the material removal rate with respect to the standoff distance, okay, or NTP, also like nozzle tip distance you can write NTD. Fine. So for that, this is a nozzle. So this is like first, second, third, and the fourth one. So this is like we are just considering this example that these are the abrasive particles, okay, which is coming at a very high velocity. Let's take an example of like uh, it is at the velocity of 150 meter per second. Okay, so these are at 150 meter per second, so they are basically impinging over the workpiece surface. So this is the first case, like we are assuming that this is below this, this is the workpiece surface, and below this there is a workpiece. Okay, so next, first we are considering this one. So only this much distance we are considering, only this much distance. So if just assume that this is the SOD1, this is the standoff distance 1, and this is like you can consider this is in the range of 0.7 mm to 1 mm. Okay, this is 0.7 mm to 1 mm if this the standoff distance is like that. Okay, so this is the distance between the nozzle tip and the workpiece surface. Okay, so as it will this abrasive particle which is coming at very high velocity. So why I made this graph, this red color one, because if this abrasive particle is coming out from this nozzle, then basically they will try to spread the area because it is already at very high velocity. Okay, so they will basically try to spread in like this direction. Okay, so when you will see from the top bottom view, then it will be a circle in a form. Okay, so when it will impinge over the workpiece surface, we have already discussed that it will be formed like a semi-sphere. So this semi-sphere will be looks like this. Semi-sphere will be looks like this. If you will see the here, the important thing is the diameter of this semi-sphere, the diameter of this semi-sphere. Okay, so when we are considering the standoff distance in the range of 0.7 mm to 1 mm, the diameter will be equals to d1, I'm saying that is in 0.4 mm. Okay, that is 0.4 mm. Okay, now just we are increasing this standoff distance from this is the nozzle tip, and from here to this is the second standoff distance. So we have increased, so this standoff distance will be equals to like we can say 5 mm. Okay, so this is 5 mm. So from here, now from here to here, from here to here, so when you will see the shape of this semi sphere, then it will looks like this. Okay, so this is the sphere. Now here the diameter, obviously you can see from the first one to second one, the diameter is increases. Okay, so this diameter will be equals to 0.6 mm. Okay, now let's see, let's increase this standoff distance from 3 to 4. Okay, at 3 it will looks like this, and at 4 it will looks like this. Okay, so this is the diameter is increasing because this spread of this abrasive particle is increasing. So wherever it will come in contact, they will basically remove the material. Okay, so this is the second case. Like this is the third case, when this standout distance is increases from SOD will be equals to 10 mm. Okay, and this is SOD will be equals to 15 mm. So this diameter will be at this will be equals to 1.5 mm, and at this D4 will be equals to 2 mm. Okay, so this diameter. Now here you can see that here the question can be raised that there is a possibility that this total volume will be same. Are you getting my point? Please concentrate that the total, there is question can be raised that the total volume means if you will see this one, then this is the small in this semi-sphere. We are just assuming that this will be in like the volume will be like that will be the volume will be equals to this one. Okay, it's not like that. The volume is reduced in the first case is high. Okay, let's suppose it's if we are increasing this standoff distance, then it will try to become like high. Okay, but as you are going beyond the limit, it will try to become less. Okay, by the way, it is at the beginning it is like deep pattern that is formed under the workpiece surface, but as it will move from the workpiece surface, from the nozzle SOD increases, then this will become shallow means wide, we can say. Okay, this is the wide. In this direction the diameter is increasing, so that they are trying to become wide, not the deep penetration. The deep is increasing. Okay, so here if you will see that graph for this okay, this is the SOD. Okay, and this is the MRR, that is material removal rate. Okay, so now here guys, that just try to assume that this is the minimum gap. Okay, and as we are increasing the space, so just try to assume that as we are keeping very less, because this SOD in the range of 0.5 mm to generally it is 5 mm, we can say. We are maintaining this one. Okay, we are, why we are maintaining this one, that is also important, because I discussed with you guys in the process parameters, that is in the range of 0.5 to 5 mm. So initially, like this is the nozzle tip distance, so we are keeping, so is like the abrasive particle which is releasing from this nozzle, immediately they are impinging over the workpiece surface. Okay, immediately means they are not getting a gap to impinge that, like as they are coming out, they are directly colliding with the workpiece surface. Like this kinetic energy cannot be converted, this high energy, the velocity, which is velocity will be increases, like by the way these are moving with a very high velocity inside only, but it will increases little bit, it will increases when it will come in contact with the atmosphere. Okay, so as atmosphere means as it will come out, that time the velocity will increases this kinetic energy. Okay, so this kinetic energy, as it is just coming out, the kinetic energy is less, because number of particles are there, and these number of particles within a small very cross sectional area is impinging over the workpiece surface. But here I cannot say this is an impingement, they are just colliding. Impingement means with some distance is there, and with that distance only these abrasive particles is impinging over the workpiece surface. Okay, but here is not actually, it is like this. Here just they are coming out and they are just spreading in the environment. Okay, there is a one more possibility because of that this advantage. If you will keep this distance very minimum, if you will keep this distance as minimum as possible, then what will happen, whatever the abrasive particle which is just colliding over the workpiece surface, they will basically try to contact or remove, they will try to contact means after. Okay, so here is the this abrasive particle is coming. So if once it will collide over the workpiece surface, where it will move, it doesn't mean that it can move in this direction, always move in this direction, and this particle will move in this direction. There is a possibility that this particle can be impinged over here as well. So there is a possibility to removal of the material from the nozzle, means the life of the nozzle is decreases. So for that also we do not maintain this very minimum gap. Okay, so if it is in the like 0.7 to 1 mm, then the material removal rate, obviously the material removal rate is increases. But as you are increasing the distance, obviously now the impingement will start. So if the impingement will start, then only the like material removal rate start increases. Okay, but if you will see that, okay, this is first, up to first you can say this is the standoff distance, this is the second. Now as you are increasing this standoff distance, now if you are keeping this one, means initially it was here, now you are keeping this one, then there is a possibility. But if it is here, if this gap is increases like this, then in this case, this whatever the abrasive particles they are coming at a certain distance, we can say there is an impingement because they are coming with a very high velocity and they are colliding with the workpiece surface with a high velocity. So we can say they are impingement. But if you will increase this distance, then what will happen, that whatever the abrasive particles, they are basically spreading, they are covering the they are increasing the cross sectional area. If they are increasing the cross sectional area, it means that whatever the abrasive particle which is coming in this region, okay, out at the periphery, they will not remove the material, they will just shower over the workpiece surface. Only the abrasive particles which is at the center, they will only try to remove the material. That's why we are making this figure like this. Okay, means here the maximum, the abrasive particle which is following this path, they will only remove the maximum material, rest it is decreasing, rest it is decreasing. Okay, so please keep in mind, if we are increasing the distance, standoff distance, then after some time this material removal rate start decreasing. Okay, the same will happen if you will continue to increase this standoff distance, it will be decreases. Okay, so this is second one, this is third one, this is fourth one. Okay, so if we are increasing up to the certain distance, then it's fine, so that is acceptable. So that will be like, we can say like, this is for the second condition, this is maximum. For the third condition, it start decreasing, we are increasing the SOD. So this is the distance, this is the graph for the material removal rate. Okay guys, so one more thing, then I after that you can ask me if you have any doubt. Like if you will see the graph of all three, then in all three cases the material removal rate initially is increasing, then it start decreasing. Okay, here I want to discuss one more thing in the abrasive flow rate. Is abrasive flow rate, as I mentioned, that we are just increasing the quantity, but in other words, like we can say okay, not here, but okay, I can discuss here. Let's suppose that if we are increasing the there is another parameter, that is, as I said, that there is a many characteristics. Okay, there is a many things, but I just discussed these are basic. There is a one more thing is there, that fourth one, which is the like material removal rate with respect to versus the size of the grit. Okay, or abrasive grit, size of the abrasive grit. What is the meaning of sizes? Like if we are maintaining this SOD, standoff distance, okay, this is the workpiece, and we are maintaining the first one, this is the standoff distance, so that is in the range of 0.7 to 1 mm. Okay, so let's suppose that we are using the abrasive particles of same size. Same size means, like, just assume that 10 micrometers of the abrasive grits are coming from here and they are impinging over the workpiece surface. So obviously if it is 10 micron, then we can say like they are covering some space over here. Okay, they are covering over some space. Okay, so they are removing the material. So just assume that you are now from 10 to 20 mm you are using, 10 to 20 mm you are using, you are increasing the diameter of the grit. So because size of the grit is defined by the diameter of the grit only, dg. Okay, so it means that initially we are using this one, sorry, this green color one, just assume that this is the abrasive part, abrasive grits we were using. Now we have increased the diameter, now we have increased its diameter, and this shape is become like this. Now just increase one more diameter, that is the third one. Now which where is the possibility that maximum material removal rate is there? Maximum material removal rate, if you will see this one, then for such kind of abrasive particles you have to impinge 10 or 15 or like more than that. Okay, in the same abrasive particles, if you are increasing the size of this, then these are the very high, like abrasive, these are the abrasive abrasives only, so they will remove the material as comparatively with this one. Like here, if you just assume that यहाँ पे अगर आपका 10 abrasive particles you are using very with a very small size, then here it will one or two will be remaining these material from the workpiece, same amount of the material from the workpiece. So what we can do here, what we can conclude is, if we are increasing, if this is the material removal rate and this is dg, so if we are increasing the size of this material this abrasive grids, then the material removal rate is increases. But please keep in mind that we have to constant this SOD at that time. Now just uh, now let's suppose, okay, up to this is 10 micron, this is 20, this is 30, let's make it 50 or 100. Okay, so just make it 50 or 100. Okay, So this is just make it 50 or 100. So you have to see this area as well at this time. Okay, you have to see this area as well. Now, by the way, this from the nozzle, this abrasive particle has been removed, but the distance is has been completely covered by this abrasive particle. You getting my point? This space, which is a space between the nozzle tip and the workpiece surface, that is completely covered by this abrasive particle. So where it will impinge? There is no space to impingement. As it is coming out, it is directly jumping over the workpiece surface. Means, like, just try to assume that this is the abrasive particle and this is the nozzle, okay, and this is the workpiece. So it is just coming out from the nozzle only. Okay, so it is like just where the space to impingement. For the impingement there is a necessity to for the gate, but there is no space. Okay, that's why we are increasing the standoff distance, and here this by increasing the standoff distance the material removal rate is increases. Okay, but here if you are increasing this abrasive size, grid size, then there is no space for the impingement. So after some time, we have, if we are maintaining a constant standoff distance, then after sometimes the material removal rate is decreases. Yes, so after some time it is decreases. So for that also it will be like a same kind of same characteristic, means same kind of graph. Okay guys, so please just concentrate this one. Okay, yes. Now guys, any one of you have any doubt, you can ask me. There is, this is mixing ratio we have already discussed along with the that process parameters. Okay guys, so there is no need to discuss here. So if you have any doubt, you can ask me. From my side, the theory part of this abrasive jet machining is over. Okay, now we are going to going over the numerical problems. So if you have any doubt, you can ask me. If there is no problem, then let's move to the next one. First problem. Okay, guys. So this is the first problem that has been asked in the gate examination in the production engineering in 2007. That in abrasive jet machining process, the if Q is the flow rate of the abrasives. Here guys, we are discussing if nothing like flow rate is not mentioned, then we can consider two things. First is like mass flow rate, or we can consider volume flow rate. Okay, so but it is about the abrasive grids, so we are just AG, just write AG. Okay, this is abrasive grid. Okay, then D is the mean diameter of the abrasives. So guys, can you tell me that which relation, which is where the material removal rate is proportional to? This MRR will be proportional to. Okay, what will be the relationship? It will be Q by D square, Q into D, Q into D square, or D into, it's not D, it's Q into DQ. Can you tell me guys which relationship it will be? Okay guys, so please concentrate. Like here two things is mentioned, that one is mass flow rate or volume flow rate we can say, and second is the diameter. Okay, so let's go to the formula that we have derived. So first, for the brittle one, okay, if you will see the for the brittle, then this material, for this one, let's suppose this one, that this is the mass flow rate is mentioned. Okay, but here this is the velocity, this is rho g, and this is h. The diameter is not mentioned. Okay guys, so the diameter is not mentioned. So let's go to the another formula also we have in terms of delta and dg. So here if you will see, then this is the mass flow rate. Okay, this is the mass flow rate is given, and this is delta, this is rho g, and this is dg, means dg is the diameter of this abrasive grid. So here for the brittle, these two things are available. Let's suppose, let's consider for another one as well. Okay, let's suppose for this one, this is for the ductile. So if you will see for the ductile, then this is the mass flow rate. Okay, this is the mass flow rate, that is mg. Okay, it's given, and this is dg. Okay, this is dg square is given to you. And if you will see this one in terms of mass flow rate and v square and h, here the diameter is not the diameter term is not available. So for the ductile, okay, for For the brittle, for the ductile, let's suppose this mass material removal rate is directly proportional to m dot g upon d square, and for the in case of brittle, it is proportional to m dot g upon d power 3 by 2. Okay, so I'm just writing over there that in case of the brittle material, it is directly proportional to m dot g upon dg raised to 3 by 2, or in case of the ductile material, it is directly proportional to the m dot g upon dg square. Okay, so here m dot g here is represented by the q, so this is q upon diameter of the mean diameter of the abrasive, so this is d raised to 3 by 2, and for this is q by d square. So guys, for if you will see that this is, by the way, here it's not mentioned that which material it is. Okay, for which material it is saying us. Okay, so let's suppose first, if it is a brittle material, then it will be q by d to the power 3 by 2. So is there any option is available? No, there is no such option. Okay, let's suppose it for the brittle ductile material, so it will be like q by d square. So this is q by d square, so the option will be a. It is q into d, it is q into d square, it is q into d cube. So these are no option, there's only option a is correct. Okay guys, so this is the option a. Okay, so let's move to the next problem. This okay Okay guys, so this is the problem, like estimate the material removal rate in abrasive jet machining of a brittle material. See guys, so for the brittle material, the material removal rate is given as is directly proportional to the m dot g, v to the v is there, rho g is there, 1 by 4, this is 3 by 2, and this is h, which is 3 by 4. Okay guys, so I think this is the formula. Yeah, this is the formula. So this is let's see what is given to you. The flow strength is given to you, that is flow strength means the hardness is given to you. So h is given to you, that is 4 gpa. If I reduce that into newton per meter square, then this will become 4 gigapascal. Giga means 10 raised to power 9. Okay, so this is 4 into 10 raised to power 9, that will become pascal, and pascal we can write that is 4 into 10 raised to power 9 newton per meter square. This is newton per meter square. Okay, next is the abrasive flow rate, that is m dot g. Okay, so this is m dot g is given to you, that is 2 gram per minute. Okay, next is the velocity, that is v is given to you, that is 200 meter per second, and the density of the abrasive grids, that is rho g, that is given to you, that is 3 gram per cc. Now before like we have this formula where the m dot g is given to you, this is m dot g, v is given to you, this is v, this is rho g is given to you, and h is given to you. So we just have to put the value and get the answer. But guys, please listen, here we are just converted that into newton per meter square, here it is in gram per minute. So why we are calling, we have to convert it, because this is newton. Newton is what? That is mass into acceleration, and mass means the kg we are considering. Okay, that is kg into meter per second square. So just convert this term into the kg first. Okay, and here it is in minute, but here it is in second. So either you should convert that into the second, or this one into the minutes. Okay, so just before putting the value, just convert that. One more thing is here, that here this value is also in gram. So first convert that into the kg, and this is in cc. Cc means cubic centimeter. Okay, cubic centimeter means semi cube. Okay, so here we are using this into the meter square, and it is in semi cube. So just convert this into the meter cube. Okay, just convert everything into the SI unit, then put the value, then get the answer. Okay, so in the next lecture you will tell me the what exactly the answer you are getting. Okay guys, or you can paste into the Google Classroom as well. Fine. By the way, I have explained all the things, that you just have to simply calculate this only. Okay. Okay, guys. So let's move to the next problem. This is the last problem in this lecture as well as in this topic. So I'm going to do this. Okay. So okay. So during the abrasive jet machining, okay, the mixing ratio used is 0.3. Mixing ratio is MR, that is equals to 0.3. And if I say simply define that mixing ratio, then mixing ratio will be equals to the volume flow rate of abrasive grids, the volume flow rate, the volume flow rate of abrasive grids upon the volume flow rate of air or gas, we can say. Okay. Next is calculate the mass ratio. By the way, mass ratio I have not discussed yet, so I will just explain you here. If the ratio of density of abrasives, okay, so the what is another term is given to you, ratio of the density of the abrasive to the density of the gas means rho abrasive grids upon rho of air or gas, we can just assume, so that is equals to 30. This is given to you. So what we have to calculate, we have to calculate the mass ratio. Okay, so the mass ratio, please do not write by mr because otherwise it will be confusing, because here mr we are writing with the uh, mixing ratio. Okay, so this is mass ratio, this is represented by the alpha, and that will be equals to the mass flow rate of abrasive grids upon the mass flow rate of the abrasive grids upon mass flow plus mass flow rate of air, means mass flow rate of the abrasive grid with respect to the total mass in the mixture. Okay, this is the mass ratio, because here the completely the material removal of the workpiece is depend on the abrasive grids. Okay, by the way, that depends on the air as well, the pressure that is the pressure through which the air is passing, so that is also important, but that we have already seen in the mixing ratio. Okay, so it's like if so we have to write it, we just have to like convert this one. Okay, so this is the mass flow rate of abrasive grid, so mass in terms of density and volume, can I write? So this will be equals to rho of abrasive grids into volume of abrasive grid. Okay, or volume flow rate, you can say. Okay, and this is rho of ag abrasive grid, volume flow rate of abrasive grids plus mass flow, sorry, density of air and volume of air. Okay, so this is alpha, so I'm just cross multiplying this one. Okay guys, so just I'm keeping this value over there, and just look at here that this is rho of ag, v of ag plus rho air into v air upon rho of ag vag equals to 1 by alpha. Okay, now if you will see the left hand term, then that will be equals to, this will be like 1 plus this will be rho of air upon rho of ag into v of air upon v of ag. Okay, now here from here this 1 by alpha equals to 1 plus 1 by, like, sorry, rho of air upon rho of ag. So here rho ag upon rho air is given to you, but here it is asking rho air upon rho ag, so that will be reciprocal of that, means 1 by 30, 1 by 30 into this is v air upon vag, but here it's given to you that is mass ratio, mixing ratio, that is v of ag upon v air, so again it will be a reciprocal, so this will be like 0.30. Now can you tell me the value of alpha guys from here? Come on, calculate and tell me.
It's around 4.3333.
The value of alpha, Aman?
No, sir, 1 by alpha.
Okay, 1 by alpha. Then just get the value of alpha.
So it's 0.230.
0.230. Guys, please cross check this value. Okay, man. So what is the value of alpha that you are getting?
0.230.
230. Okay. So I'm just asking the random one. So Ibad, what are you getting? Or 1843 Muslim, what are you getting? The value of alpha. Please tell me. Gibran, rather Gibran. So you also tell me the value of alpha from here. Guys, if you are sleeping, then I will not count your attendance. Danish, you can also answer.
The same.
0.230.
0.2301.
2301. Okay.
So 0.90.
Majid, what are you getting?
So 0.90.
Please speak loudly. I'm not. You are not audible.
So 0.90.
0.90. Right. Guys, if you will just like, if you will see from here, like this is 1 by alpha and this is 1 plus like 1 by 30. Okay, and it is simple calculation. So this is, I'm just removing this point sign. So if this, I'm just removing this point sign, then after the point there is two values. Okay, so this will become 100 by 30, right? So this will be cancel out and this will be cancel out. Okay, so 1 plus how much remaining, this is 1 by 3 from here, and here is also 1 by 3. So 3 into 3, that is 9. This is become 1 by 9. Okay, and when you will take the LCM, this will become 9 plus 1 and it will become 10 by 9. So this value is equals to 1 by alpha. So from here this value will be 9 by 10, or it will be equals to 0.90. Okay, so this is the answer. Aman, please, Aman and Danish, please check
Yes,
this
sir.
answer.
Yes,
This is
yes,
not
sir.
the
I
exact.
was actually I was adding what divided by 38, what divided by 3. It
Okay,
was
okay, okay.
multiplied. Sir.
Maybe it has multiplied. Okay, okay, guys. So this is not the exact value. The value of this alpha is equals to 0.90. Okay. So thank you so much, guys, for all this attending all these sessions. And just I'm